Alright, here is the solution to question 11 on Newton's Law practice problems. So what we have is a 25 kilogram box on a table connected by rope and a pulley to a hanging 15 kilogram mass. We're given coefficients of static and kinetic friction, and we're asked to find the tension in the rope just after the system is released. So I've started two free body diagrams, one for each of the masses. So let's look at the first one, the 25 kilogram mass. This mass is sitting on the table. So there are some forces acting on it. The first is, since it's on the table, there's a normal force, which is in the positive y direction, and there's a weight, which is downwards in the negative y direction. There's also the tension in the rope pulling the box to the right, and there's a force of friction which is opposing the motion. So let's label some of these. So here's the tension, this is the weight, here is our force of friction, and our normal force. Alright, one thing to note here is that the magnitudes of the weight and the normal force should be equal, because this box is not going to accelerate up or down. Alright, now let's look at mass 2. There's only two forces, the first being the weight, and the other being the tension in the wire. Now, this tension, although it's in a different direction, its magnitude is the same as the tension in the other free body diagram. So I'm just going to call this, well, I'll call this one T1 and this one T2, but they have the same magnitude. And here we have weight, I'll call that weight 2, and the other weight, weight 1. Right, so here are our free body diagrams. So where do we go from here? Let's look at mass 1. So mass 1, we'll consider the forces in the x direction. So for M1 in the y direction, we have the magnitude of the normal force, that's the y component, and the y component of the weight is minus the magnitude of the weight. And we know that this should sum to 0 because it's not moving. It's not going to move in the y direction. So solving for n, sorry, that should be a W2. Solving for n, and the magnitude of the normal force should equal the magnitude of the weight. I don't know why I put 2 there. It should just be 1. There we go. Let's change it to 1. 1. So this is M1 times 9.8. Here we're going to use G as positive 9.8 meters per second squared. Okay, so here is the magnitude of the normal force, which means we can figure out the force of static friction. So the magnitude of the force is equal to, well, first of all, what's going to happen? What's going to happen when we release this system is that the tension force is going to pull mass 1 to the right. So the box is going to accelerate to the right, which means that our force of friction is actually kinetic friction. And so we have the magnitude of the kinetic friction is the coefficient of kinetic friction times the magnitude of the normal force. So we have mu k m1 g. Okay, so in the x direction, we have the following. We have the negative of the force of friction plus the tension force should equal, from Newton's second law, mass times the acceleration in the x direction. This should be a T1. Note that the magnitude of T1 should equal the magnitude of T2, and we'll just call this T, so we can drop the subscript 1. Alright, so there's our first equation. So let's look at mass 2. So for mass M2, 2. We only have two forces. They're in the y direction. The magnitude of T2 is just T, and it's upwards, and the y component of W2 is going to be minus M2 times G. And this is going to equal M2, this one over here should be M1, M2 times the acceleration in the y direction. Now, one thing to note about AX and AY in these two equations, so this term and this term, is that AX should equal minus AY. They should be the same acceleration, but one is going to be negative because it's going in the negative y direction. So for our second equation here, I'm going to write it as T minus M2G is equal to minus M2AX. Okay. Let's call this equation over here 1 and this equation over here 2. What I'm going to do is I'm going to subtract equation 2 from equation 1. And on the left-hand side, you can see when we do this, the t's are going to cancel. So we're going to get minus the force of friction, the magnitude of the force of friction, plus M2G, that comes from this term over there. And this is going to equal M1AX plus this term, well, actually it's minus this term, but the two minus signs are going to give you a plus, M2AX. There we go. Simplifying the right side, we can write this as the acceleration in the x direction times M1 plus M2. And what we want is, we actually want to solve for AX. So AX is going to equal M2G minus our static friction force divided by M1 plus M2. Okay, static friction we showed up here was mu K M1G. So we have M2G minus mu K M1G divided by M1 plus M2. Okay, plugging in the appropriate values, you should find that AX should be 7.96 meters per second squared. So that is our x acceleration, and since we know the x acceleration, we can actually solve for t. We can either use equation 1 or equation 2. Let's use equation 2. So from 2, we get the tension is equal to M2G minus M2AX. So M2 we know is 15 kilograms. We have G is 9.8 meters per second squared minus 15 kilograms times our acceleration, which is 7.96 meters per second squared. And what we find is T, the magnitude of the tension force, I believe should be about 50.5 newtons. And our original problem, if we go back to the top, is to 2 sig figs. So we can round this to 51 newtons. Okay, so does this answer change if we give the box an initial velocity? So that's this part here. If we give this box a little bit of a shove, Well, if we give the box a shove, no, because we used the coefficient of kinetic friction, so nothing is going to change. The tension of the force is still going to be the same. Okay, that's it.